In this video, I will be talking about modeling the deterioration behavior based on visual inspection data. My name is Zachary Amida, and the work I'm about to present has been published under the title Modeling Infrastructure Degradation from Visual Inspections Using Network Scale State Space Models. Now first, what are visual inspections? Visual inspections is a monitoring technique that's utilized on a large scale to monitor the deterioration behavior of infrastructures over time. In our case, these infrastructures are really the bridges. So, if we look at the image on the right hand for this bridge with the ID 002, at a given year, 2017, the structural components of this bridge are inspected through visual inspections. Now, we represent the structural components with the small letter e, whereby the subscript refers to the structural element ID, and the upper script refers to the bridge ID. Now, the visual inspections at year 2017 can be represented by a single point on this timeline. And normally, visual inspections are performed once every year up to once every 4 years. So for this particular case, we have 3 inspections. And again, this is a large-scale monitoring technique. So we have visual inspections from many bridges. In our case, it's really 10,000 or more than 10,000 bridges. So with the global picture in mind, let's look at a single structure element and how the inspections would look like. On this graph, on the x-axis, we have the timeline, which is on a yearly scale. On the y-axis, we have the structure element health condition. So it's ranged from 25 for the worst possible condition up to 100 for structure element in perfect condition. The inspection data are represented by the blue points, and each blue point is associated with the letter I and an ID number. These refers to the inspectors responsible for the evaluation. Now, by looking at the data, we are expecting a deterioration, so from better health to worse health. And this is not the case in the data shown here. And this is because of the subjective nature of visual inspections, which is a point that we're going to come back to later. But it's just to highlight that here we are not, here there's no maintenance or repairs that have occurred that resulted in such a trend. So, in general, our objectives in working with visual inspection data is really to model the deterioration behavior based on visual inspections from a network of bridges. Now, within this, we aim to quantify the uncertainty of inspectors performing these visual inspections, and we aim to estimate the deterioration rate. Now, the proposed framework that we have is that we propose to model the deterioration behavior based on kinematic model. This kinematic model is described by the well-known kinematic equations for the condition, the speed, and the acceleration. Now, to put these equations into matrix form, we have these components where we have the xt, vector xt, the state at time t. A is a matrix, and xt minus 1 is the state at t minus 1. Wt is the process noise. Now, the method that would enable us to employ such a model is really state space models. Now, state space models is described or characterized by 2 models. The first one is the transition model, which, if you notice, it's exactly the same kinematic model that's shown above, where we have xt equals a xt minus 1. A is the transition matrix, and Wt. Now, the process noise, or Wt, is described by normal distribution with a 0 mean and Qt, which is the covariance matrix. The second model in state space models is really the observation model, where we have yt, which is the observation, equals to c, the observation matrix, multiplied by xt, which is the state at time t, plus vt, which is the observation error. The observation error is described by a normal distribution with a zero mean and a variance rt. Now, looking back at the example that we've shown earlier, again, if we look at the inspection data, we notice that each inspection point has a different inspector. And this is, again, coming back to the point that the inspections are really, visual inspections are really subjective, which has been also documented in the literature. So from this, we can conclude that the uncertainty of the observations is really dependent on the inspector responsible for this evaluation. Now, in order to account for this, what we propose to do is to modify the observation model. This is the observation model that we've shown earlier. If we look at the observation error here, if you look at RT, now this observation error, if we use it for the case of for visual inspections, if we use the same RT, then we are saying that all the inspectors has the same error, which is not the case in visual inspections, again, as documented in the literature. So that's why what we propose is really to associate a variance term for each inspector. So we would have as many variance error variance for the observation error as we have inspectors. And these are going to be model parameters that are going to be estimated for the whole data, which we will see in the later slides. So another challenge also we have with visual inspection is that the uncertainty of the observations, again, if we look at the structural element shown in the picture on the left hand, we can tell with high confidence that this structural element is in a poor condition. Also, if we look at structural element in new bridge and new structure, we can tell with high confidence that this structural element is in a perfect condition. However, for cases that are in between, it becomes really more challenging to determine the deterioration state. So that's what we refer to as the gray area between the two extremes. For the worst possible deterioration condition, where we have 25 health condition, up to the best possible health condition 100. The cases that are in between these, they are difficult to determine, and that's why we expect to have a higher uncertainty. That's why we say that the uncertainty of the observations may depends on the deterioration state. So in order again to account for this is that we need to perform a space transformation. This space transformation can be done through a transformation function. However, this transformation function needs to have a certain characteristics. First, we need to have the uncertainty dependent on the state. So the transformation function can't be fully linear. It has to have nonlinearity. Second, my deterioration condition ranges from 25 to 100. So I can't see my model providing me with a deterioration condition estimate of 110, while I know that the condition should never exceed 100, and the same thing for the 25. I never expect my model to provide a value less than 25. So that's why my transformation function should be a step function. Now, how does this transformation function look like? Let's look at this example. So the transformation function is really shown in the upper right corner, where we refer to it by the transformation function g, and we have these parameters that describe it. Now, this is a step function. If we look at the figure in the lower right corner, figure A, we see there are two states. One is a continuous line, the other one is a dashed line. Now let's focus on the continuous line. if we pass the, first, the state with the continuous line is really centered near a value of 75. So if we pass this state into the transformation function, we get what we see in the continuous line, figure B, on the left upper corner. We see the continuous line PDF. So it's fairly similar to the continuous line in A. And this is because this PDF is really the state is really within the linear margin or of the transformation function. But if we look for the second case, for the dashed line, where we have the state is centered near the lower bound, 25. If we pass this state in the dashed line in figure A, the lower corner, right corner, if we pass the dashed line into the transformation function, we get the transformed PDF shown by the dashed line in figure B. So you would notice that the tip of the PDF became higher, and the uncertainty and the spread of the PDF became lower in figure B on the upper left corner. So it's different. The PDF is different, and this is what we really expect from the transformation function. So here, to set the terminology, the transform space is really the unconstrained space, and this is, we refer to it by X. The original space is really the constrained space, and this is, we refer to it, we use tilde to refer to anything in the original space or in the constrained space. Now, having all these components in mind, let's look at the full picture of the model. So for a given bridge, out of the set of the bridges in the network, and for a given structural element in this bridge, we have the inspection data in the original space, which is y tilde. Now we pass this inspection data into the transformation function g, and we get y. Now we have the transformed inspection data, which is unconstrained from minus infinity to plus infinity. Now, what we do is that we pass it into a Kalman filter. Now, the Kalman filter would use the kinematic model to predict, and we would use the observation model to update, and so on. So, however, we still need to make sure that that we are modeling a deterioration, that is a downward trend, and that's why we have to constrain the speed to be negative. So after each time step of a Kalman filter, we check for the constraints, that is if the speed is greater than 0, if the expected speed plus 2 standard deviation is greater than 0. If it is yes, then we apply the PDF truncation. If no, if the speed is negative, then we carry on business as usual. Now, the PDF truncation method, what it really does is that if I have a state that violates a constraint that I have, then what it does is really truncate this state to be within the feasible domain. So we update the state in case of constraint violation. Now the same thing is also for the Kalman smoother. After the Kalman filter, we have the Kalman smoother. We also check after time step to make sure that we are modeling a deterioration behavior. Now, after the Kalman filter and the Kalman smoother, we have the states at each time step up to time t capital, which is the time window of the analysis, and then we have these states in the transform space. We back transform them to the original space for the interpretation. So this is the full framework. The Kalman filter also, not to forget to mention, that provide me with the log likelihood for each observation. So having all this deterioration model framework, this framework, this model has parameters. And these parameters are summarized in this set, theta, where I have sigma b's referring to the inspector's standard deviations, sigma w referring to the process error standard deviation, n, the transformation function parameter, which really controls how much nonlinearity I have at the edges. The details of the transformation function and how this transformation function parameter affect are really detailed in the paper itself. And we have the initial state, which is here we parameterize the variances or the standard deviations of the initial state. Now, there are some challenges, is that my time series is very short. I have 3 observations or maybe up to 5, but that's it. So that's why my initial state would have a significant impact on this time series. Another thing is that my data is highly noisy, and this is because, again, the subjective nature of visual inspection data. So that's why we try to further investigate what is best suited to, or how can we get the best outcome from modeling from the initial state. And in this, we through experimentation, we found out that it's better suited to model the variance of the deterioration speed as a function of the condition of the deterioration. And that is described by the equation shown here, where we have p1 squared, which is a parameter, p1, and multiplied by u, which is the upper bound for the health condition, for example, 100 in our case, minus mu c1 tilde, and this one refers to the condition at time step 1, and plus p2 squared, where we have, it's also another parameter. So my initial state would be described by these parameters for the speed and for the other condition and acceleration. So these are for the parameters. Now the parameter estimation, how is it done? It's done through the MLE, or maximum likelihood. So we have the log likelihood as estimated through the log likelihood for all the observations in the time series for all structural elements in the bridge, for all bridges. So this is what the log likelihood function formulation looks like. And our optimal parameters are obtained through maximizing the log likelihood subject to the parameters feasible domain. And in this case, really, like, all the standard deviations should be, or variances should be, positive, and the n parameter has integer values. Again, the details for this are really available in the paper for the full parameter estimation framework and further details about the parameters. Now, this is the model, this is the parameter estimation and the parameters of the model. We need to verify the performance of the model. In order to do so, we've generated synthetic data that is as much similar to the real data as possible, and whether quantitatively or qualitatively. And we made sure quantitatively is that we have the same number of structural elements, which is 10,827. Here, structural element refers to a time series, really. And the same number of inspectors providing these inspections or observations, 194 synthetic inspectors. Now, the details of how we generated the synthetic data, again, are really available in the paper. So, if we examine one structural element of the synthetic data, and we look here on the x-axis, we have the timeline on a yearly scale. On the y-axis, we have the health condition or the deterioration condition of a structural element. And we have these inspection data represented by the blue points. Now here, it appears to be, there are two opinions about the health state of the structural element or the deterioration state of structural element. So There are two inspectors that are within the 90s, and there are two inspectors within the 80s. Now, it's unrealistic to have a steep deterioration within this short period of time. So that's why, if you're modeling the realistic deterioration behavior, who would you trust out of the two sets? The inspectors on the left hand or the inspectors on the right hand? Or in this case, it's one inspector on the right hand. So in order to answer this question, you need really to know how much uncertain each of these inspectors is. So this is provided through the parameter estimation framework that would enable us to quantify what's the inspector uncertainty. So we have the inspector uncertainty represented by the blue vertical line. And as you would see, the inspectors on the left really have a better accuracy or less uncertainty around their observation given the inspector on the right. So that's why our deterioration model would gravitate toward the inspectors on the left hand, as you would see here, where we have the dashed line, red dashed line, represent the deterioration condition at each year. And we have the red areas around it represent 1 and 2 standard deviations. Now, since this is synthetic data, we have access to the true deterioration state, and which is represented by the black dashed line, as you would see here. And you would notice that the true deterioration state is really within the confidence interval of our model. So this is for time series analysis. Now, for the inspectors in general, or the quantification of the standard deviations of the observation error for each inspector. So on the x-axis, we have the true inspector sigma v. Again, this is synthetic data, so we have access to the truth. And on the y-axis, we have the estimated inspector sigma v. Now, if our estimation is perfect, the point should land on the diagonal, the red diagonal you see on the graph. And as you can see that the points are really aligned with the diagonal these points are really estimated through the parameter estimation framework, and they show a good alignment with the diagonal, which confirms the performance of the parameter estimation framework. Now, the dashed line you see near the value of 3 is really the starting point for optimizing, or the initial point for all sigma v's of all inspectors. So this is for the inspectors. Now, if we want to evaluate the model forecast performance after 1 year, so following the last inspection after by 1 year, we look at the true condition on the x-axis versus the forecasted condition on the y-axis. And again, if I am perfect, I should land on the red diagonal. And as you can see, the scatter plot here for population of structural elements, we see a really good alignment with the diagonal. Now, if we go farther and in time and we take a forecast for 5 years, again, x-axis true, y-axis forecast, we see that the scatter plot is also well aligned on the diagonal with a little bit more spread, but it's still a really good performance. And if we go even farther for 10 years, we see like really the alignment still consistent over time with the diagonal for true versus forecast. Now, this is for the verification with the synthetic data. Now let's go to the real data. Now here we have a time series taken from a real case. The timeline is on the x-axis, so yearly scale, and the condition of the structural element is on the y-axis. The inspection data are represented by the blue points, and the inspectors, same thing we have. So the parameter estimation for the uncertainty of these inspectors is shown by the blue vertical line, as you'd see here. And the model prediction and forecast over time is represented by the red dashed line with the red areas representing 1 and 2 standard deviations of the model forecast. So this is in the real case, and what we did is that we've hid one of the observations. So there's an observation that has not been used in the training or in updating the model. And this observation is shown by the red asterisk with the inspector I21. And as you would see, that the model was right on point in forecasting the observation, and the observation generally lies within the confidence interval of the model. So this is for a case that shows a kind of consistency. If we go to a more challenging case where we have 3 inspections again, and the timeline again on the x-axis, the condition is on the y-axis, and the uncertainty associated with each of these inspectors is represented by the blue vertical line, the model prediction and forecast by the red dashed line. And if we also again we consider the same thing, is that we've hid one of the observations and now we add it on the plot. And as you can see, this observation that was never used in training the parameters or in updating the model prediction is within the confidence interval of the model. So now if we consider this case, if we want to examine a population of real structural elements, and we want to look at the forecast versus a hidden observation. So the red asterisk observation, the new inspection point, versus the forecast, and see how are they differing. So for 1 year we have very few cases, and as you'd see, this graph we have on the x-axis is the model forecast, and on the y-axis we have the new observation. And this is really similar to what we are showing here, is that if we take the slice of 2018 and we are comparing the forecast versus the observation. So this is what we have if the new observation, the hidden one, was 1 year after the last observation. This is what we have if the hidden observation was 2 years after the last observation. So the hidden observation is really something that wasn't used in the training. And as you see, there is an alignment on the diagonal, but however, I don't need to land on the diagonal because I'm comparing forecast to observation. So there is uncertainty. So this is for 2 years. This is for 3 years. Also, we see a good alignment, and for 4 years, we see a good alignment. Now, what this graph really tells is that the bias in the model is really in the model forecast is insignificant, provided that we are seeing the alignment around the diagonal is in both directions. It's not like deviated toward one direction versus the other. So this shows that there is very little or insignificant bias in the model forecast over time. Now that's it for the real inspection data. There are further analyses that are available in the paper. For conclusion, what we've done here is that we proposed a deterioration model for network scale visual inspection data. The uncertainty of visual inspections is quantified according to the inspectors performing the evaluations and according to the deterioration state of the structural elements. The predictive capacity of the model is verified and validated with synthetic data as well as real data, respectively. So this is for the work. All the details, further details, are really available in the paper. The paper would be available in the description of this video. Thank you so much.